Assalamualaikum warahmatullahi wabarakatuh and good day to everyone. In this video, we are going to discuss on chapter 4 magnetic field, transformer and motor. In the first video, I'm going to discuss on the first part of magnetic field and transformer, and later we are going to discuss on the topic of motor. We had learned the basic of electric circuit in the past lectures, and remember that in a conventional circuit, the current will always flow in either direction or either way. Next, we also had heard about the permanent magnet, a magnet that has a north pole and south pole. A permanent magnet can attract any other metal object. The other characteristic of a magnet is that the opposite poles are going to attract each other while the same pole are going to repel. Permanent magnet can be in different shape, and the magnetic field of the permanent magnet can't be stopped or paused, and this is one of the reasons why it is called as permanent magnet. Next, we can have any metal with a magnetic domain. The magnetic domain are pointing at random directions, making no magnetic field. But when we take a wire and we coil it around the metal and run electricity through it, we are going to get an electromagnet. Similar to permanent magnet, an electromagnet has north and south pole, and it can attract other metal objects. But unlike permanent magnet, the magnetic field of an electromagnet can be turned off by stopping the current. The direction of the field of a long straight wire. So we had learned that electromagnets are going to be created when we have electricity running through a wire or a coil. So how can we decide the direction of the magnetic field? So using the right hand rule, okay, we can easily use our own right hand. First, we have to grasp the wire in our right hand and then point our thumb in the direction of the current. So in this figure, the direction of the current is upward, and then your fingers will curl in the direction of the field. So using the right hand rules, we can understand that the magnetic field is flowing in the direction of our fingers. The magnitude of the field at a distance r from a wire carrying a current of I can be given by this equation, where B is equal to mu naught times I over 2 pi r. So the value of mu naught or mu 0 is given by 4 pi times exponential of minus 7 Tm over A. An electromagnet consists of an iron core placed inside a wire coil. The magnetic field strength of a wire coil carrying an electric current increases in direct proportion to the number of turns of the coil. We have learned about electromagnet and how it works. Next, we are going to learn about transformer. So a transformer is an alternating current AC device which are used to change high voltage low current AC into a low voltage high current AC, and vice versa. And this is going to happen without changing the frequency. So in brief, a transformer can transfer electric power from one circuit to another circuit, and it does so without a change of frequency. And all these are accomplished by using electromagnetic induction. And electromagnetic induction is where the two electric circuits are in mutual inductive influence of each other. Transformer is being used at different kind of applications. Okay, some of them is in impedance matching, okay, for electrical isolations. And the third one is the most common, where transformer is used as AC power transmission, where we are going to have a step up transformer and a step down transformer. So based on induction theory, The transformer's behavior can be observed from this equation where epsilon, or the electromotive force EMF in volt, is equal to negative n, the number of turns of the wire, times the differentiation of the magnetic flux over time, d phi b over dt. Okay, the differentiation of the magnetic flux over time. Next, we are going to understand how a transformer works based on the induction theory. So in this figure, we have two different circuits. Okay, the first circuit is the primary, and we have the second circuit, the secondary. And these two circuits are connected by an iron core. So we are going, the transformers only works with an AC supply. So we have voltage of the primary VP, and at the iron core of the primary circuits, we have a primary coil with a number of coil NP, and at the secondary circuit we have a secondary voltage Vs and the secondary coil given by Ns. So when current in the primary coil changes being alternating in nature, a changing magnetic field are going to be produced. This changing magnetic field gets associated with the secondary circuits through this iron core, where the flux and the iron core is going to be uh, transferred or connected to the secondary coil. Hence, the magnetic flux linked with the secondary coil are going to change. And these changes in the magnetic flux are going to induce the electromotive force in the secondary circuit. As I had mentioned previously, a transformer is being used as a step down transformer or step up transformer, where in our current power grid system, the power generation and transmission depends a lot on the usage of transformer. Where at the power station, okay, they are going to produce a very high voltage of electricity of 400 kilovolt, and this voltage are going to be stepped down, okay, at several station, okay, in order to transfer the electric through a longer and wider area. So from the power station, it is 400 kilovolt, okay, where we have the station here are going to step down the voltage to 130 kilovolt, where the current, where the electric are going to be transferred or transmit to a different area. One part is for the industry, where they are going to use a 33 kilovolt of voltage in the industry. But for small industry, they are going to use 11 kilovolt. But for residential area like our home, okay, the 11 kilovolt are going to be stepped down to a much lower voltage, which is 240 volt. And you can see this kind of station or structure near your residential area, okay, or your housing area, where we have the TNB substation, where inside this structure will be a lot of AC devices and of course transformers. Next, we are going to discuss on the transformer models. So imagine we have an ideal transformer, where an ideal transformer is where all the currents and voltage are going to be efficiently 100% transferred from the primary circuit to the secondary circuit. So in an ideal transformer, In the primary circuit, we are going to have the voltage across the primary VP, primary current IP, and number of coil or number of windings in the primary circuits NP. And similarly, we are going to have NS, the number of windings in the secondary circuit. We have IS, the current for secondary circuit, and VS, the voltage across the secondary. So this is the models or the circuits that shows an ideal transformer where all the currents and voltage are going to be transferred using inductive and the power given by V times I are going to remain the same. Now let's take a look at the relation between primary and secondary. So turns ratio, or also known as A, is defined as the ratio of the number of turns in the secondary windings N secondary or NS to the number of turns in the primary windings N primary or NP. So we are going to have this relationship where VP over VS, okay, the voltage of primary or voltage of secondary, is equal to the ratio of number of windings of the primary over the number of windings of the secondary. And this is unequal to the currents of secondary over the current of primary. And this equation can be represented by the turns ratio A, where we have when A is less than 1, it means that it is a step up transformer. Okay, meaning that the secondary voltage are going to be higher than the primary voltage. While if the A is larger than 1, then it's going to be a step down transformer, meaning the secondary voltage are going to be lower than the primary one. Voltage and current angles are not affected, therefore theta P equal to theta S equal to theta. So in real life, okay, the transformer are going to have losses. Okay, it's not going to be ideal. Okay, we are going to have power loss somewhere in the circuit of the transformer, and these losses must come into consideration while we are calculating for our transmission of the electric power and so on. So the main three losses of power inside a transformer caused by the first one is copper losses, okay, given by the loss due to the resistive characteristic of the copper, given by this equation I square times R. And then the second loss is caused by the leakage of the flux, and the third loss is caused by the core, where we have two different factors, which is the eddy currents and the hysteresis losses. So let's take a look at a real transformer model and where does these losses occur. So in the primary circuit, okay, the copper losses, okay, caused by the resistive characteristic of the wire copper, okay, given by Rp, resistance of the primary Rp, and then we have leakage flux, okay, caused by during the induction Lp, and then we have the core losses, okay, where we have the eddy currents and hysteresis losses, okay, all have due to the resistance Rc and the induction J times M. And in the secondary circuit, okay, we are going to have similarly the leakage flux losses and the copper losses, okay, caused by the secondary wire. There are several types of transformer, and the first types that I'm going to discuss is the auto transformer. An auto transformer is used to change a desirable voltage by only a small amount. For example, from 120 volt to 130 volt. So this is a step up transformer. So the circuits are going to be shown like here. We have the low voltage or the primary circuit and the high voltage or the secondary circuit. Second type is three-phase transformers. Three-phase transformers can be constructed in two different ways. The first way is using a three-phase bank, which consists of three single-phase transformer. So we have three different single-phase transformer. And the other way is to use three windings wrapped around a common core. So we are going to have a three-phase transformer but using one core. So the first is three different core. Second one is just one common core. A three-phase transformer connection being done using four different method. The first one is from delta to Y. Okay, we have look at this. We have discussed or learned about the delta and Y in the previous lecture regarding the resistor. And then we have a delta connection. Then we have a Y to delta connection. So Y to delta. And we also have Y to Y connection. So four different transformer connection for a three-phase. Previously, we had discussed about the power loss in a transformer. Therefore, we have to know or calculate the efficiency of a transformer as an AC device. The efficiency or eta, given by this symbol eta, is the ratio of the power out to the power in of a transformer. So power out will be the secondary and power in is in the primary. So this is the equation of eta, power out over power in. So eta in an ideal transformer will have no power losses, meaning that the power in is given or defined by the equation of power V times I times the angle. So we have Vp, voltage of primary, times the current of the primary, and the angle of the primary, theta p. And the power out is given by Vs times Is times cosine theta s. So an ideal transformer will have P in equal to P out, which means that Vp Ip cos theta p is equal to Vs Is cos theta s, and therefore the eta for an ideal transformer should be 100%, or equal to 1. Obviously, a real transformer will have a value of eta less than 100. Next, we also have the terms voltage regulation. So voltage regulation is the ability of a system to provide near constant voltage over a wide range of a load condition. So it also compares the output voltage at no load NL to the output voltage at full load FL. So smaller value of voltage regulation is usually beneficial, indicating that the line is closer to the ideal. So regulation is the ability to maintain the speed or voltage constant in the face of load variations. The ability to closely regulate speed in a motor or voltage in a generator is a very important feature of electric machines. And regulation is often improved by means of feedback control mechanism. So an ideal transformer, so we have a voltage regulation is given by this equation where the voltage at no load minus the voltage at full load over the voltage at full load, remember that this is all the output voltage times 100%. So an ideal transformer will has a voltage regulation VR equal to 0. And for motor, okay, we are going to use different terms, which is speed regulation, but the equation are still the same. That's it for our lecture on the first part, electromagnet and transformer. We are going to continue with the second part on motor in a different video.